Thank you for the introduction. Good morning, everyone. I'm Rohan Gandhi from Purdue University, and today I'm going to talk about Rubik, a network-friendly load balancer at cloud scale. So this is a joint work with collaborators from Purdue University and Microsoft. Today, online service providers like Microsoft, they host large number of online services in their data center. For example, Bing.com and OneDrive. Individually, these services run on hundreds or thousands of servers. Load balancer is a critical component in this infrastructure to provide high availability and scalability to online services. Typically, each online service is assigned a set of virtual IPs or VIPs that they use to receive traffic from outside the service. Internally, each server in the data center is assigned a single unique direct IP or a DIP. Load balancer stores VIP to DIP mapping for all the VIPs, and it uses this mapping to split the incoming VIP traffic across DIPs assigned to individual services. This way, by providing an abstraction of a virtual IP, load balancer hides all the details from individual services. And this way, it helps provide high availability and scalability to online services. And because of these benefits, many internal services talk to each other through load balancer. Ananta, a software load balancer, which was published in SIGCOMM 2013, is one of the popular ways of doing load balancing. Ananta spreads hundreds or thousands of software muxes throughout data center. Individually, software mux run on a commodity server, and the web traffic coming from the clients is first forwarded to the software muxes. The software muxes then use the VIP to DIP mapping to split this VIP traffic across DIPs and forward it to DIPs. But at cloud scale, Ananta is very costly. In a 40K server data center, it would take almost 10% of all the servers just for load balancing, which is too costly. Duet, which was published in last year's SIGCOMM, reduces the load balancing cost by almost 24 times. And it does that by using commodity switches. Duet stores VIP to DIP mapping in the switch memory in the TCAMs. And because switch memory is limited, it partitions the VIPs across multiple switches. The switches announce the VIPs using BGP to receive the traffic for the VIPs assigned to them, and it then splits the VIP traffic across DIPs and forwards it to DIPs. But because the switch memory is limited, Duet is not able to handle all the traffic using switches, but it still handles almost 97% of the traffic. And for the remaining traffic, it uses software muxes from Ananta. But both these designs cause traffic redirection. And the problem is worse in Duet. Because Duet assigns one VIP to only one switch, traffic from many sources first has to travel many different links just to reach this switch. And after load balancing, the traffic going to the DIPs again has to travel many different links to reach individual DIPs. So even if sources and DIPs are located under same tower in the same rack, the traffic has to go out of the rack just to reach the load balancer. And this has a negative effect on the network. To understand the implications of this redirection, to understand how bad the dark side of this redirection is, we compare Duet against a hypothetical case we call shortest path. So in the shortest path, the traffic is forwarded to the DIP that is closest to the sources without using any indirection. And we see that Duet inflates the path length by almost 3x compared to shortest path. More importantly, Duet inflates the max link utilization to 97%, which means there is congestion in the network. And compared to shortest path, the max link utilization is almost 12 times. And lastly, Duet inflates the total traffic in the network by almost 3.7 times, which is not good. So now, Duet having this dark side, the problem remains on how do we build a low cost and robust load balancer without burning the network. And for that, we propose Rubik. Rubik is based on two key ideas. First, it exploits locality. It brings load balancer closer to where the sources and DIPs are located. And second, it exploits endpoint flexibility, where it moves DIPs closer to where the sources are. So in the next few slides, I'll show that using these two principles, we reduce the path length between sources and DIPs, which help us reduce the link utilization. So Rubik's first key idea is to exploit locality. So if you recall, Duet assigns one VIP to a single switch, and it will more often or not be far away from many sources and DIPs. But there are opportunities where there are DIPs located in the same rack as the servers. So if we move the load balancing to those racks, we can contain all the load balancer traffic in individual racks itself. So this traffic doesn't have to go beyond links, beyond top of the rack links, and that could help us reduce link utilization. So Rubik's first key idea is to exploit such locality to contain the load balancer traffic in individual racks itself. Rubik's second key idea is to exploit endpoint flexibility. So even if we move load balancing closer to the sources, the dips could still be located far away. So traffic still has to take longer paths to reach the dips. But we observe that there are cases where there are dips located in the same racks as the sources. But it's just that the dips are currently assigned to other WIPs. So if we can migrate the dips so that we bring the dips closer to the sources, again we can contain all the load balancer traffic in individual racks. So this Rubik's second key idea of exploiting endpoint flexibility is synergetic with its first idea. It only creates more opportunities to exploit locality. So with these two key ideas, the natural question is, can we actually localize all the traffic? Can we actually contain all the traffic in individual racks? And as I'll explain in next slide, the answer is no, because we have limited resources. So Rubik's first goal is to maximize the total traffic it localizes. And Rubik's second goal is to make load balancer highly robust against individual failures. And that's because the availability of online services directly depends on the load balancer. So first, we examine on whether we can localize all the traffic in individual racks. And to be able to do that, we would need enough servers to handle the traffic, and we would also need enough switch memory to store the WIP to DIP mapping for all the WIPs whose traffic is generated in the racks. In reality, both these resources have limit. So it can happen that the switch memory is full, or it's not enough to store all the WIPs whose traffic is generated in the rack. It's also possible that we don't have enough servers. Either the servers don't have the capacity to handle the traffic, or it just simply the servers are assigned to other services. And lastly, it could happen that we have a smaller number of dips than the number of sources. The number of dips is typically specified by the customers, and we could have cases where there are more sources. So in this example, let's say we only have 3 dips to place, and there are 4 sources. So there is no way we can localize traffic from all the sources. But that's not the end of the world. So from a traffic trace from our production DC, we see that for individual WIPs, the traffic coming from different racks is highly skewed. Some sources generate more traffic than other racks. So even if we can localize traffic for the racks that have large volume of traffic, we can still reduce the total traffic entering the data center network. So in Rubik's evaluation, we show that Rubik is able to handle almost 63% of the traffic locally, even if it covers only 42% sources. So those were the key ideas in Rubik. So now let's dive into how we actually implement, how we realize these ideas. So first, to be able to localize the traffic in multiple racks, we split the WIP to DIP mapping for a single WIP into multiple local mappings and a single residual mapping. So first, I'll explain how we exploit the locality, assuming the DIP placement is fixed and given. Later, I'll show how we exploit endpoint flexibility. So let's say in this example, we have 3 dips and we have 4 sources. So to exploit locality, we first split the WIP to DIP mapping into multiple local mappings and single residual mapping. Local mappings are assigned to the top of the rack switch, and they only handle the traffic generated in those racks. So in this case, the traffic in rack 1 and 4 is handled by the local mappings across dips present in the same rack. So this way, this traffic doesn't go beyond links beyond top of the rack switch. But as we have limited resources, we might not be able to handle traffic for all the sources. For the sources whose traffic we cannot localize, we use a single residual mapping. So residual mapping is assigned to any switch in the network, and it announces the WIP using BGP so that the sources whose traffic we could not localize goes to the residual mapping switch. It then uses the WIP to DIP mapping to split the traffic and forward the traffic to the remaining dip. So now if we have enough resources to localize traffic for all the traffic coming from all the WIPs, that would be great, but we don't have we don't have enough resources, and now we need to choose on for which WIPs we assign, how do we assign the local mapping, how do we assign the residual mapping, and now we also need to decide how we place the dips, how we exploit the endpoint flexibility. So in Rubik, we formulate a assignment problem that maximizes the total traffic that we localize, and it calculates the local mapping, residual mapping, and dips to do that. And we calculate these mappings so that we don't violate we don't violate the capacities on individual resources, and at the same time we also don't want to create hotspots where some dips are overutilized, where other dips are underutilized. And lastly, we calculate these assignments so that we limit the dip migrations, because the dip migrations could affect the transient availability of online services. So in Rubik, we calculate these assignments in 2 steps, as I'll explain in next few slides. In the first step, we assign the local mapping and dips simultaneously, and in the second step, we assign the residual mapping. So in the first step, we assign the local mappings and dips together. That's because the problem of assigning local mapping and dips is intertwined. To be able to handle traffic locally, we want enough servers and we want enough switch memory on the switch. If one of these two is missing, we won't be able to localize the traffic. And as a result, we assign local mappings and dips together. So in the first step, the objective of the algorithm is to maximize the total traffic that is localized. And we formulated a linear program, an LP, to do that. So the input to the LP includes topology of the network, traffic sources, and number of dips for individual WIPs. And it also includes the capacities of individual servers and switches. We calculate the assignment with following constraints: that the capacities on individual resources is not violated, we don't create hotspots, we assign the number of dips specified by the customers, and lastly, we keep the number of dips migrated under limit. So we formulated an LP to place the local mappings and dip, and in practice, it is pretty fast. On a 500K VM data center, it could calculate these mappings under 5 minutes. So details on the LP are in the paper. So once we place the dips and once we place the local mapping, the question remains on how do we place the residual mapping. So the residual mapping, we use residual mapping to handle the traffic, which we could not handle through local mappings. So in this step, the objective of the algorithm is to calculate residual mapping so that we maximize the total traffic that is handled by the switches, by the residual mapping. So this problem, this assignment problem is similar to the problem that was in Duet, which is to maximize the total traffic while satisfying the individual switch memory constraints. So we use the same heuristic algorithm as Duet, and which we detail in the paper. So in practice, we find that local mappings handle almost 2/3 of the traffic, so there is only a small fraction of the traffic going to the residual mapping. So now changing the gears, Rubik is also, the Rubik's second goal is to make load balancer highly robust. It should be able to handle traffic even when individual local mapping and residual mapping fails. So when local mapping fails, it's not a problem actually, because when the TOR fails, all the sources and dips under it also disappear. So it doesn't affect the availability of the service. But when the residual mapping fails, the traffic going to the residual mapping is now black hole, and this could potentially affect the availability of the service. So Rubik needs to handle the traffic when the residual mapping fails. And we do this by using software muxes as a backstop. So in addition to using switches, we spread a small number of software muxes to handle the traffic during failure. So these software muxes run on commodity servers. So when the residual mapping fails, the traffic is routed to the software mux closer to the sources. And the software muxes then route the traffic back to the dip. And we use the same algorithm to choose the dip for both residual mapping and software muxes so that the existing connections are not broken. So we evaluated Rubik using a testbed setup, which included 20 switches in 4 different containers. We implemented our testbed using OpenWiz switches and Mininet. Through testbeds experiments, we showed that Rubik is highly robust against failures. The details are in the paper. And in the second part of the simulation, in the second part of the evaluation, we used large-scale simulations using topology and traffic trace from one of our production data center to show that Rubik actually reduces the max link utilization and total traffic, as I'll explain now. So first, we compare max link utilization for 4 different designs. We compare it for Duet. We compare it for a design called Rubik LO, which only exploits locality. We compare it for Rubik and also for shortest path, which is optimal. We observed that Rubik LO is able to reduce the max link utilization by almost 2x compared to Duet, and Rubik further improves it because it exploits both locality and endpoint flexibility. So finally, Rubik is able to reduce max link utilization by almost 4 times. And both Rubik and LO and Rubik are able to do this because they localize a large fraction of the traffic. Rubik LO is able to localize on average 35% of the traffic. So this is based on the traffic trace we collected for 24 hours. And Rubik localizes almost 46 to 72% traffic locally. On average, it is 63%. In the last part of the evaluation, we compare the total traffic for Duet, Rubik LO, and Rubik. We measure the total traffic in core links as well as container links. And we divide the total traffic into baseline and overhead. The baseline includes traffic without any indirection, and overhead specifies the overhead because of the redirection. So we find that Rubik LO is able to reduce the total traffic by almost 2 times, whereas Rubik reduces the total traffic by almost 3 times. And the same is true for both core links and container links. So one thing to notice here is Rubik doesn't completely eliminate the overhead. Because there is still some traffic going, there is still some redirection because the traffic is going through residual mapping. Rubik is not able to completely eliminate the overhead. So with this, in this work, we built a Rubik, which is a switch-based load balancer with a very low network overhead. And we reduced the network overhead by exploiting locality and endpoint flexibility in placing the dips. Together with these 2 ideas, we are able to reduce the max link utilization in the network by 4 times and the total traffic by almost 3 times. And the ideas or the principles used in Rubik, they're just not limited to a load balancer, but they can also be exported to any other cloud scale mid-box designs. Thank you.
Hi, Andrew Hume from Ericsson. I'm a little confused about what the nature of the traffic is. This is a load where all the cost is in transmitting, the data to be processed, and there's essentially no cost in processing it.
Probably I didn't get the question. Can you repeat it?
You've concentrated completely on transmission of data around the network.
Yes.
And you've not given any consideration, or it never seemed to come up that it might cost some time to actually process it? Is the processing time essentially 0 here?
The processing time is very small because the switch is processing in the hardware, so the processing time is in microseconds.
So you're shoveling all this data all around the place, but you don't ever actually do anything much with it?
So the latency, the major part of
Sorry, you're sending the data to an endpoint. What does the endpoint do with it?
Oh, the endpoint is a regular server.
Is a regular what?
Is a typical server.
Yeah, but, okay. So what does it do with it?
It's the application that decides what to do with the data that is coming in. So let's say it's a Bing.com, so it will decide what to do with the request that is coming in.
But you get my point, right? If it spends any time processing it, then you wouldn't think the network load would be the dominant thing.
Maybe we can take it
okay.
offline. Yeah, sorry.